Welcome to Topology class. Today we will discuss about topological spaces, some more examples. Last class we have discussed the example of topologies on real numbers. Today also we will discuss the same. That means topologies on R. So last class we have discussed topological spaces or topology. That's better. Topology on R. Topologies on R. First the thing we have considered is first example was R with usual topology. With the usual topology. Second one was R with semi-open interval topology. Next we will discuss this much we have discussed already. Next we are having example 7 as scattering topology. Scattering topology on R. Set of real numbers. So in order to define a topology, it is enough to define the open sets. So the open sets in this topology are of the form A union B, where A is an open subset of R, in the usual topology, and B is any subset of the rational numbers. Irrational numbers. Let me correct it. Any subset of the irrational numbers. So this is the topology. The resulting topological space is called the scattered line. It's called the scattered line. So what does this topology means? Let us see. In this topology means, first of all we are mentioning this topology in set of real numbers. So we are having the real numbers here. Now in this topology we are taking all the subsets of the form A union B, where this A is a open subset of R in usual topology. So usual topology, what should be the open subsets of R? All should be open intervals. So this A means of open intervals of the form A comma B. Now what about B? B means set of or subset of irrational numbers. So irrational numbers means we will have lots of examples. So we're having if tau represent if tau is scattered topology, then 1 comma 2 an open set, right? Union root 2, this is a member in tau, right? Similarly, you can have minus 1 comma 3 union pi, it should be another member. So like that members, we will say that this is a scattered topology, and the resulting topological space, that is R with a scattered topology, is called a scattered line. Now note, every subset of irrational numbers of irrationals is open. What's the reason? Every subset of irrational is open. So every subset of irrational open means if I am taking, so consider pi. Pi is a subset of irrational, right? It is a subset of q minus. If I am denoting with q minus, is a irrational. So this is a subset of irrational numbers. But I can write this as empty set union pi. Okay, so pi can be written as empty set union pi. Now in usual topology, this phi belongs to usual topology, and phi belongs to usual topology on R. So this implies that set pi is open in scattered topology, or which belongs to scattered topology. Thus, I have taken only singleton set pi. So if you are having the same way, you can say that root 2 is also belongs to the scattered topology. And if you are taking root 2 union pi, that again belongs to scattered topology, since the net topology is closed under arbitrary union. So like that, if I am proceeding means it will contain all the irrational numbers. Okay, so any subset of irrational number is open. Consequently, no sequence can converge to an irrational number. except and eventually constant sequence. Eventually constant sequence. The problem is that suppose you have got a sequence in which root 2 and the term is root 3 and the name is root 2, root 3, etc. So this sequence may converge to either root 2 or root 3 or some other thing, okay, or some c. Now suppose my sequence, this xn I'm mentioning, this xn converges to root 2. What will happen? If xn converges to root 2 means I'll have the set root 2, singleton root 2, which belongs to my topology, and infinitely many terms are lying outside of this open set. So that means our sequence cannot converge to but root 3, which is infinitely times occurring, does not belongs to singleton set root 2. So it cannot converge to root 2, which implies xn cannot converge to root 2. Same way you can say that it cannot converge to root 3. And in the same way, if it is converges to C, then also infinitely many terms are lying outside the singleton C. So anyway, this sequences cannot converge to any of these irrational numbers except the eventually constant sequence. Next example, example 8. Again, in R, another topology can be obtained by taking the empty set phi comma the whole set, that means the entire real numbers, and all intervals of the form A infinity times, where A belongs to R. Okay, I'm taking empty set, all the set, and intervals of the form A infinity where A belongs to R. This topology is much weaker. This topology is much weaker than the usual topology on R. Now, what about the convergence of sequences? Convergence of sequences. Convergence of sequences in this means consider the sequence some eventually constant one. So it is A, etc. Any open set, containing A is R or of the form some A minus R comma infinity times. Therefore, what will happen? Which implies constant sequences converges. Thus, eventually constant sequences converges, right? Constant sequences converges. Suppose if non-constant sequences, suppose a non-constant sequence, that will be A, B, etc. And suppose A is less than B, then the sequence converges to A. Sequence converges to A. Since the reason is when you're taking the open set containing A means it should contain either R or A infinity form, right? Or A minus R infinity form. Now since A less than B, definitely all the B's should be contained in this set. Okay, so if there are lots of repetition or lots of terms is coming, if you're going for the minimum of these values and finding that minimum means the sequence may converges to that minimum value. Thus, a sequence xn converges to minimum value of xn if it exists. If it exists. So this is the convergence part of the sequence. Next we will see example 9. Example 9. Let X be a linearly ordered. Let X be linearly ordered by less than or equal to. Now a subset A of X is open if for each X belongs to A, there exists A comma B belongs to X such that A less than X less than B and the interval AB is contained in A. For this, assume that X has no smallest, and no largest element. and no largest element. X be linearly ordered by the order relation less than or equal to. Now a subset A of X is open if for each X belongs to A, there should exist A comma B belongs to X such that A less than X less than B and the interval AB is completely contained inside A. For the time being, assume that X has no smallest and no largest element. It is called the order topology. It is called the order topology induced by the order induced by the order less than or equal to. Induced by the order less than or equal to. As a note, in R we have got a usual ordering, that is A less than B, right? 1 less than 1 less than 2, 2 less than 3. This is called the usual ordering. Now, in this ordering, we can form a topology. Okay, and that topology coincides with the usual topology. In R, the topology induced by the usual ordering coincides with the usual topology. Coincides with the usual topology. Next we are having the 10th example. Example 10. This is called Serpensky Space. SIERPINSKI. Serpensky Space. So any set with two elements, any set with two elements AB, any set with two elements AB, where A not equal to B, the topology consists of empty set, singleton set A, and the entire set. So this will form a topology, evidently, right? So suppose you are mentioning this as some Ts is equal to, so we are having X equal to some AB, and we are defining phi is equal to empty set X and singleton A. Will it form a topology? First we want to check whether empty set and entire set belongs to this topology or not. Yes, it belongs to. So first condition of topology is satisfied. What about the second condition? It should be closed under arbitrary union. So when you're taking union with the empty set and X, you will get X. x and a, again you will get x. So arbitrary union also it is closed. Next you want to take whether it is closed in a finite intersection. When you're taking intersection with empty set, you will get empty. And when you're having intersection with x and singleton I, you will get this to be as a. So in finite intersection case also, it is closed. So definitely it will form a topology. Now the importance of this topology is that this is the smallest topology not induced by a metric. So this is mark Serpensky space space is the simplest example is the simplest example of a topology of a topology not induced by not induced by a metric, not induced by a metric. Next we will pass to the next example, last example of the session, example 11. It's a particular type of topology. Let n be the set of natural numbers. Let n be the set of natural numbers consider the Cartesian product n cross n. For k belongs to n, we shall call the subset n cross k as the kth row of n cross n. Kth row of n cross n. So what do you have to do? You should consider n cross n. So n cross n first I am naming as this is 1 1, okay, 1 2, okay, I'm mentioning not in this version, check in this version, 1 1, next is 1 2, 1 3, etc. Here 1 1 1 2 1 3, I'm having 2 1, okay, 2 1, 3 1, 4 1, etc. Here 2 2, 3 2, 4 2, etc. Here 2 3, 2 3, 3 3, 4 3, etc. Suppose like that I am mentioning, what should be here coming as some k element n cross k. N cross k means second element should be always k. So here second element is k means somewhere here will come. Okay, so this should be 1k, right? 2k, 3k, 4k, etc. So n cross k. So my n cross k will define this row. So what is the order of this row? 1, 2, 3 extra kth row. So this is my kth row. So it is the meaning of this. So in this n cross k is the kth row of n cross n. Now we'll insert a symbol. Let is not infinity, it is closed alpha. Let this closed alpha be any symbol not in n cross n, not in n cross n. Let x equal to n cross n union this closed alpha. Okay, x equal to n cross n union closed alpha. Now we shall define a topology. We shall define a topology on x. What is x? N cross n union closed alpha as follows. As follows. And a topology on x as follows. Let tau1 or t1 be the power set, be the power set be the power set of n cross n. So we have the power set of n cross n. Then clearly this tau1 is contained in power set of x. Let tau2 or t2, let script t2 be the collection of those subsets A of x such that closed alpha belongs to A and A contains almost all points. A contains almost all points in almost all rows. That means if T2 be the collection of those subsets A of x such that closed alpha belongs to A and A contains almost all points in almost all rows. That means suppose you are mentioning like this is the representation. Now if I am taking something like this, see this set I am considering, so extending up to infinity, right? So if I am considering this set, what I should have? I have got almost all points from almost all rows, right? So like that set, and this set contains the closed alpha also. In such a case, we will say that set to be as A. So A is a subset which contains closed alpha and almost all points from almost all rows. Now let T equal to T1. What is T1? Power set of n cross n union T2. If we defining like this, then the script T is a topology on X. Okay, we are not moving to proof of this, just we are stating that this will form a topology. So today we have discussed about examples of topological spaces on R. First one was the scattered topology. Second one, a special topology whose subsets are or the sets in the topology are of the form empty set, entire real line, and subsets of the form A infinity, where A belongs to R. And next one, we have discussed the ordered topology. And next, Serpensky space. And remember, it is an example of the smallest topology which is not induced by a metric. And in n cross n, we have defined one topology. In n cross n, we have defined one topology, namely taking x equal to n cross n union some closed alpha, which is a symbol not in n cross n, and define the topology as tau equal to T1 union T2, where T1 is the power set topology of n cross n, and T2 is the collection of those subsets of n cross n union or X such that our closed alpha belongs to A and which contains almost all points in almost all rows. And now this will form a topology. With this, I'm winding up today's session here. Thank you for your patient listening. Thank you.